The radar picture looks like a swarm of angry bees, except each bee is a drone with a small engine, a cheap camera, and one job: get close enough to ruin a billion-dollar ship. The ship does what it always does. It starts spending missiles, one perfect intercept at a time, like throwing gold bars at pigeons. In your mind, you can almost see the counter ticking down. 90 cells, 60, 40, 20, and then the worst number in modern naval warfare, 0. The terrifying part is not that the ship runs out of weapons, it is that the ship runs out of time, because swarms do not arrive politely. They arrive all at once. They overlap, they confuse, they multiply, and they dare you to keep paying full price for every tiny target. This is Battletech Declassified. Modern Warfare Explained. Now imagine the same swarm, same weather, same stress, same screaming alarms, but instead of hearing the hollow click of an empty launcher, you hear a generator groan and a deep electrical hum, like a stadium floodlight turning on. A turret slews, invisible energy reaches out, and one drone starts failing in midair, not with an explosion, but with a quiet collapse, like a phone that suddenly dies at 1% battery. This is the promise of lasers. Ammo becomes electricity, your magazine stops being a pile of missiles and becomes a question: how much power can you make, how much heat can you dump, and how many seconds can you hold a beam on target before the next threat arrives? That is the flip from Season 2's saturation math into Season 3's future weapons reality. Season 2 was the nightmare equation. Missiles are great until you do the math. A drone can cost anywhere from cheap enough to mass produce to still cheaper than your interceptor. And the Defender's missile is almost always the expensive answer because it has to be perfect. It needs guidance, a motor, a seeker, a warhead, a safe storage life, a launch system, and a logistics chain. In saturation, the attacker is buying lottery tickets. The defender is buying insurance policies. And even if you have a high kill rate, you can still lose because your cost per kill is too high and your magazine is too finite. That is why swarms are not just a tactical threat. They are an economic weapon. They force you to spend yourself tired. Lasers sound like the cheat code. If a missile is a single-use bullet, a laser is more like a rechargeable drill. It does not get thrown away after one hole. It just needs electricity. In theory, the cost per shot becomes the cost of fuel, maintenance, and wear, instead of a whole new missile. In theory, the defender stops playing, count the missiles, and starts playing, keep the lights on. But here is the first rehook. Lasers do not make defense infinite. They just move the bottleneck. You stop running out of missiles, and you start running out of something else. Clear air, stable tracking, cooling capacity, and most importantly, time on target. The swarm is still trying to overwhelm you. It is just overwhelming a different part of your system. To understand why lasers change the math, you only need a simple picture. Imagine you are defending your house from 1,000 ping-pong balls being thrown at your window. Missiles are like paying someone to catch each ball with a custom glove. Expensive, precise, and limited by how many gloves you own. A laser is like turning on a powerful heat lamp that can melt the ping-pong ball before it reaches the glass, as long as you can keep the lamp pointed at it long enough. That last part matters, because lasers are not magic zap beams most of the time. Many kills are about dwell, holding energy on one spot until something critical fails. So the real question becomes, how many seconds per target can you afford, and how many targets can arrive inside the same minute? Now add the C. Salt spray, haze, smoke, humidity, heat shimmer, and the simple fact that your target is moving, bobbing, weaving, sometimes intentionally. A shipboard laser is an engineering fight against physics, not a movie prop. Systems like HELIOS are often positioned first for counter-drone work, sensor dazzling, and tighter integration with surveillance and fire control, because that is where lasers shine early, pun intended. A dazzler does not have to burn through a wing. It can blind or confuse a camera, break tracking, force a drone to lose the plot, and that can be enough to save the ship. The promise is not one beam stops everything. The promise is one beam gives you a cheaper, faster option against the lower end of the swarm. Let's talk about the ammo becomes electricity line, like a real budget. A missile is a stored decision. You bought it months or years ago, and it sits in a cell, ready but finite. A laser is a live decision. You are converting fuel into electrons, and electrons into heat on a target. So your magazine becomes your ship's power plant, plus whatever storage and buffering you have. That is why directed energy is often described as having a potentially low cost per shot, because you are not firing a manufactured object, you are firing energy. Early shipboard laser efforts already highlighted that shift, especially for low-end threats. But again, the swarm is not impressed by your accounting. It only cares whether you can deliver enough energy fast enough. Here is the second rehook. Lasers can be cheap per shot and still lose, because combat is not a spreadsheet. It is a stopwatch. If your laser needs several seconds of steady dwell to cook a drone's sensor or control surfaces, then 10 drones arriving at once can still overwhelm you. The attacker is parallel. The laser is often serial. One beam, one target, one burn at a time. So when you hear infinite ammo, translate it to reusable trigger, not unlimited capacity. Your capacity is measured in kilowatts, cooling, and track quality, and those are harder to scale in the moment than simply loading more missiles into cells. Now we zoom in on what the laser is actually trying to do to a drone. Think of a drone like a flying smartphone with propellers. It has optics, a processor, a battery, motors, antennas, and fragile surfaces. You do not need to vaporize it, you just need to make it fail. A laser can heat a sensor until it blinds, it can damage a gimbal so the camera cannot stabilize, it can warp a wing edge so control becomes unstable, it can overheat a motor controller, it can even push a battery into a thermal runaway in some scenarios. And that is why counter-drone is the first sweet spot, because drones have many weak links, and weak links are exactly what a beam loves. But the drone gets choices too. It can be small, reflective, fast, spinning, tumbling, or it can hide in clutter. It can also arrive with decoys and noise. The same Season 2 theme, confuse the picture, force hesitation. Your laser needs targeting, tracking, and a stable aim point. Otherwise, you are just drawing with a flashlight in a storm. This is why modern shipboard laser concepts are tied to integrated sensors and fire control, not just a turret bolted on top. The tech story is not just power, it is control, and swarms attack control first. So where does this land in the real world? Not the marketing slides. What we know is that a destroyer has used a shipboard laser in repeated drone-focused testing, and that matters, not because it means lasers have solved swarms, but because it shows the Navy is moving from demo to repeated reps, and reps are where the truth comes out. We also know there is a key distinction. Navies are pursuing both higher energy lasers meant to physically defeat targets and lower power systems meant to dazzle and disrupt, because blinding a drone can be as valuable as burning it. In other words, lasers are arriving in layers, not as a single silver bullet. Here is the Season 3 flip. Saturation math is no longer only about how many missiles you have, it becomes a triangle: power, heat, and time. If you can keep power stable, keep the system cool, and keep the beam on target through sea, air, and chaos, you can trade expensive intercepts for cheap, repeatable effects. That is how ammo becomes electricity. But if any side of that triangle breaks, if haze eats the beam, if the cooling saturates, if tracking gets poisoned, you are back in the Season 2 world. Except now, you are losing with the lights on. That is why the future is not lasers replace missiles. The future is lasers buy you breathing room, so missiles can be saved for the threats that lasers cannot stop. A laser is not one single weapon. It is a family of tricks that all use the same currency: light. The first trick is the quiet one. You do not blow the drone apart, you make it blind. If the drone is a flying camera with propellers, then dazzling is like shining a stadium spotlight into its eyes until the picture becomes useless. That can force a miss, break the tracking, or make the drone drift. And in a swarm, making even a few drones lose coordination can be as valuable as killing them. What we know is that navies have been fielding systems that focus on this soft kill layer first because it demands less energy than burning through structure. What we are not sure about is how consistent those effects are across different drone sensors and in messy sea conditions. What that likely means is that the early laser advantage is not a Hollywood zap. It is a low-cost way to degrade the swarm's brain before you spend your expensive interceptors. The second trick is the loud one: hard kill. You hold a beam long enough that something critical fails. A control surface warps, a motor controller overheats, a battery goes into trouble, or the airframe weakens until it tumbles. This is where the promise, ammo becomes electricity, feels real, because you are not firing a missile, you are applying energy like a tool. But here is the catch that flips the story into tension. Hard kill is usually not instant. It is measured in seconds, and seconds are exactly what swarms steal from you. So the real question becomes, can a ship turn lasers into a machine that creates time, not just damage? Because if the swarm can force you to spend too many seconds per target, then even a reusable weapon can still be overwhelmed. Now we hit the part everyone forgets when they imagine lasers. The air itself is part of the battlefield. If you have ever tried to use a flashlight in fog, you have already learned the first law of sea-air laser combat. Light can get scattered, smeared, and weakened before it ever reaches the target. Over the ocean, you get haze, humidity, salt spray, heat shimmer, smoke, and sometimes the defender's own exhaust and deck turbulence. What we know is that these conditions can reduce effective range and make aiming harder, and they can turn a crisp beam into something more like a soft glow. What we do not know from the outside is how much margin each system has in different sea states and how often crews will face laser weather that quietly cuts performance. What that likely means is that the swarm may not need a perfect countermeasure. It may only need to arrive on the days when the air does half the defending for it. This is why you should think of lasers as a tool with a range and a mood, not a constant superpower. In a clean, dry atmosphere, the beam holds together better, you can reach farther, and dwell becomes more efficient. In messy air, you may still use the laser, but you use it differently, closer, shorter bursts, more reliance on dazzling, more reliance on coordination with other defenses. That creates a new kind of operational anxiety. Not how many missiles are left, but what is the beam quality right now? And here is the rehook. Swarms do not have to beat the laser directly if they can shape the environment. If the attacker adds smoke, aerosols, or distraction fires, the laser may be forced into a narrower window, and then the swarm's old saturation math returns, only now it is saturation by weather. Let's do the time math in a way that feels unfairly simple. A missile is like swatting a fly with a spring-loaded trap. You click, it snaps. The job is done quickly, but you only have so many traps. A laser is like using a magnifying glass to burn a leaf. It works, but only if you keep the light steady on one spot long enough. That long enough is the real price tag. Not dollars, seconds. What we know is that many laser effects scale with dwell, holding energy on target until failure begins. What we are not sure about is the exact dwell time needed against different drone sizes and materials in real sea air, because that depends on range, motion, and beam quality. What that likely means is that in a swarm, the attacker will try to force target switching, because every time you switch, you reset your progress, like a video game boss, regenerating health. So the swarm strategy evolves. Instead of just sending more bodies, it sends bodies with timing. One group to distract, one to force you to swivel, one to sneak lower and later, and one to bait you into burning seconds on a tough target, while easy targets slip by. This creates a brutal decision loop for the defender. Do you commit dwell to kill one drone fully, or do you spread your attention to degrade many drones partially? If you fully kill, you risk leakers. If you spread, you risk killing none. This is where ammo becomes electricity, stops sounding like a free lunch, and starts sounding like a new kind of triage. And here is the cliffhanger. The moment you realize the laser is not replacing your defenses, it is competing for your attention. And attention is the rarest resource in a saturation fight. Now imagine you are the drone designer. You are not trying to win an honor duel. You are trying to waste the ship's seconds. So you start asking, how do I make a laser take longer? One simple trick is motion. If the aim point keeps changing, the beam cannot stay locked on a weak spot. Another trick is rotation, like spinning a pizza so it does not burn in one place. You spread heat around, and you delay failure. Another is shaping, glossy surfaces and angles that bounce or scatter light, not perfectly, but enough to reduce heating efficiency. What we know is that small changes in target behavior can change dwell requirements, and swarms can mix behaviors to create confusion. What we do not know from public detail is how well each countermeasure works against modern tracking and adaptive optics in real conditions. What that likely means is that the laser race will look like armor versus tool, not gun versus bullet, both sides iterating on how fast failure happens. But here is the honest part. Even a laser-hardened drone still has fragile realities. It still needs sensors, control, and a flight surface that behaves. It still has a power system that can be stressed, so the laser does not need to be perfect. It only needs to create enough failure often enough that the swarm loses formation and timing. That is why soft kill remains so important. Blinding and confusing can be faster than burning through structure. This also creates ambiguity on purpose, because the defender can win without dramatic explosions, and viewers often misread that as nothing happened. In reality, a drone that misses by 200 meters might be as good as dead. So here is the rehook. The laser battle may be mostly invisible in the footage, and that means the real war is in the data, in tracks, in brakes, in coordination, and in the quiet moment when the swarm stops behaving like one organism. If ammo becomes electricity, then the ship becomes a power management puzzle. A destroyer is not a magical infinite battery. It is a moving city with a limited power plant, a finite set of generators, and a long list of hungry systems: radar, computers, pumps, comms, cooling, propulsion, and now, a weapon that wants a heavy, steady draw. What we know is that high-energy systems demand not only power, but stability. You cannot have the beam flicker or sag under load. What we do not know externally is the exact operational envelope on every ship, because configurations differ, upgrades differ, and sea state changes your cooling efficiency. What that likely means is that in the middle of an attack, laser performance is not only can we shoot, it is can we shoot while doing everything else that keeps the ship alive and aware. And then comes the second hidden tax: heat. A laser is not a clean conversion. Much of the energy becomes waste heat inside the system. If you have ever gamed on a laptop and felt it turn into a space heater, you understand this problem. The ship has to pull heat away, move it through cooling loops, and dump it into seawater, and every part of that chain can saturate. So your magazine is not just fuel, it is also cooling capacity over time. This is the twist. The ship might have the power to fire the laser, but not the thermal budget to keep firing it non-stop during a long saturation event. That forces a rhythm, bursts, pauses, shifts to other layers. And here is the rehook. The swarm can treat heat like a target. If it can keep you lacing continuously, it is not only trying to get drones through, it is trying to overheat the defense until your infinite ammo becomes a forced timeout. All of this only matters if the laser can be aimed like a scalpel. That brings us back to the kill chain. Detect, classify, track, aim, dwell, assess, and then decide whether to re-engage. If your radar picture is poisoned, if your track quality collapses, the laser becomes a flashlight searching a storm. What we know is that modern defenses are increasingly about integration. Sensors feeding fire control, automation assisting decisions, and systems sharing a single picture. What we do not know is how each ship's software, crew training, and doctrine will handle the chaos of dozens of small targets crossing, merging, and splitting on the screen. What that likely means is that the laser's real advantage depends on the same thing Season 2 warned about: a clean, trusted picture, because without trust in the track, you cannot commit your seconds wisely. So the swarm attacks the picture, jamming, decoys, clutter, and simple volume. Even without fancy electronic warfare, a swarm creates ambiguity just by existing: tiny targets, short timelines, overlapping tracks. This is why lasers will not replace the need for smarter battle management, because the laser is a serial tool and battle management chooses the order of targets. The defender has to ask, which drones are leakers, which are decoys, which carry payload, which are just noise. In a perfect world, you would always laze the highest threat first, but in real life, you do not always know which one that is until it is too late. So here is the cliffhanger. Lasers may make shots cheaper, but they also make mistakes cheaper, and that can tempt commanders into spending time on the wrong targets, which is the most expensive mistake of all. Now, we build the layered defense picture. Because the future is not one weapon, it is a stack. Think of a swarm like a flood, and your defenses like dams at different distances. Long-range missiles are the big dam, expensive but powerful. Medium-range interceptors are the second dam, still costly but necessary. Guns and close-in systems are the last wall, fast, loud, and limited. Lasers fit, like a new gate you can open repeatedly, a gate that can shave off the cheap mass before it reaches the last wall. What we know is that this is the logic driving directed energy adoption. It offers a potentially repeatable option against lower-end threats, and it can preserve missiles for higher-end threats. What we are not sure about is how often lasers will be available at their best conditions during real engagements. What that likely means is that commanders will treat lasers as an efficiency layer, not a guarantee layer. And here is the retention punch. Efficiency changes decisions. If a laser can neutralize even a portion of a swarm at low cost, the defender can stop panicking early because the first wave does not automatically drain the magazine. That breathing room is not just economic, it is psychological. It means the ship can wait longer before launching expensive interceptors, and it can keep more options for later. But the attacker adapts too. It will try to force the defender to reveal its rhythm, to bait laser use, to time second and third waves when the system is hot, the crew is saturated, and the track picture is messy. So here is the rehook. Lasers do not end saturation. They change the shape of saturation, and the winner will be the side that learns the new shape faster. Let's run a timeline that feels like Season 2, but with a laser on deck. T-minus 60 seconds. Detection begins, not as certainty, but as hints, faint tracks, possible contacts, clutter. The ship must decide whether to engage early or hold fire and gather confidence, because every second spent early might be a second wasted on decoys. T-minus 30. The swarm begins to separate, some drones higher, some lower, some straight in, some flanking. This is where lasers could offer a low-commitment probe, dazzle a lead drone, test reaction, see which tracks behave like autonomous threats. What we know is that early contact management matters more than the weapon itself, because the swarm wants to overload your decision engine. What we do not know is how often automation will correctly prioritize threats in real clutter. What that likely means is that doctrine, not hardware, will decide many outcomes. T-minus 10, the saturation cliff, and now the ship must choose a mode. Do you use the laser to hard kill one leaker with full dwell? Or do you dazzle multiple drones to break formation? Or do you stop lasing entirely because you need that time for missiles and guns? The laser is powerful, but it can also become a trap, because it encourages you to fight the swarm one by one, exactly what the swarm wants. So a smart defense might use the laser like a shepherd dog, not a butcher. It pushes, disrupts, blinds, forces misses, and then hands the truly dangerous targets to missiles. Here is the hook into the next beat. The key decision is not, can the laser kill? It is, when should the laser refuse a kill, so the whole ship does not lose the minute? So what does all this probably mean for the future? In human terms, it means the defender gets a new dial to turn, not a new miracle. The dial is energy, and energy can be managed, rationed, and optimized in ways missiles cannot. What we know is that directed energy has already moved beyond theory into repeated shipboard testing and incremental fielding, and that suggests the Navy believes the trade-offs are worth it. What we do not know is how the full system performs under the ugliest conditions: heavy clutter, bad air, coordinated electronic attack, multi-axis swarms, and simultaneous missile threats. What that likely means is that lasers will win the first round against simple swarms, and struggle when the attacker makes the swarm smarter, dirtier, and more layered. And that brings us to the question we leave intentionally open, because it is the question that will decide the next decade. If a laser is a serial tool, one beam at a time, how does a ship handle a truly parallel threat, hundreds of targets in 1 minute from multiple directions, while also watching for missiles? Does the answer become multiple lasers, higher power, better cooling, or a different kind of directed energy that affects many targets at once? In other words, do lasers solve saturation, Or do they simply buy time until the next wave of future weapons arrives? In the next segments, we are going to push that dilemma to the edge, because the scariest part of ammo becomes electricity is realizing electricity can still be outpaced. Let's imagine you are the ship's commander, and someone offers you a second laser turret. It sounds like doubling your power, but it might not double your results, because both turrets still drink from the same power plant and the same cooling loop. What we know is that real systems are constrained by shared infrastructure, and that infrastructure does not scale instantly in the middle of an attack. What we do not know is how each class of ship will be upgraded, because some hulls have more electrical margin and some have less, and the fleet is a patchwork. What that likely means is that future laser warships will be defined less by the turret you see and more by the hidden plumbing you do not: generators, heat exchangers, power conditioning, and software. This is where the ammo becomes electricity promise becomes very literal. If you want more shots, you do not ship more missiles. You ship more power capacity and more thermal capacity. That is like switching from stocking a pantry with canned food to installing a bigger kitchen. The meal is still the meal, but now you can cook it continuously. The twist is that a bigger kitchen is expensive and takes time to build, which means lasers create a modernization race, not a quick fix. And it also means an attacker can target your infrastructure decisions, not just your weapons, because if they can force you into non-stop high load, they are stressing the same hidden systems that keep your laser alive. Now we zoom out to the ship itself, because lasers are not just weapons, they are power policy. Some ships were designed around older assumptions: radars, missiles, and guns as the main consumers. As you add directed energy, you are adding a new kind of demand: steady, heavy, and sensitive to fluctuations. What we know is that future surface combatants are being pushed toward more electric capacity and more flexible distribution of power, because sensors and weapons are both becoming electricity hungry. What we do not know is how quickly the fleet can be upgraded at scale, because upgrades compete with budgets, shipyard time, and operational tempo. What that likely means is that lasers will appear unevenly at first, and doctrine will matter, because ships with lasers may be positioned differently, tasked differently, and paired differently. And this creates a new fleet-level chessboard move. If only some ships can sustain heavy directed energy use, then the fleet must protect those ships like they are power nodes. You might put laser-capable ships where swarms are likely, while other ships carry the long-range missiles, and others focus on sensors and electronic warfare. That is the distributed defense concept in a new costume. The rehook is simple. If lasers become the swarm solution, then lasers themselves become a high-value asset, and the attacker will start designing plans to degrade them, not by beating the beam, but by exhausting the system around it. Heat is the villain that never shows up on camera. Every time the beam is on, parts inside the system are heating up, and the ship must pull that heat away and dump it somewhere. Over the ocean, that sounds easy. You have endless water. But the bottleneck is not the ocean. It is the pipes, the pumps, the exchangers, and the safe operating limits. What we know is that any high-power system is a thermal management problem, and saltwater corrosion, vibration, and sea state make everything harder. What we do not know is how each system behaves at the edge, because manufacturers do not publish the ugly details, and real performance is shaped by maintenance and training. What that likely means is that long engagements are where the truth lives, not the first few impressive shots. So swarms change their timing. Instead of one giant wave, they might come in pulses, forcing the ship to laze, pause, laze again, and never fully recover thermally. This is like making someone sprint repeatedly with no full rest. Eventually, even the strongest runner slows down. The key choice for the defender becomes rhythm management: when to use the laser hard, when to use it soft, and when to hold it back to avoid thermal exhaustion. That creates a suspenseful trade. Every time you hold back, you risk leakers. Every time you commit, you risk a forced cooldown at the worst moment. All of this depends on one thing Season 2 already warned about: the picture. Lasers are picky. They need a track you trust, because you are placing energy precisely on a moving aim point. If you aim at the wrong thing, you do not just waste money, you waste seconds, and seconds are everything. What we know is that swarms create track clutter, false confidence, and overload, even without fancy jamming. What we do not know is how often automated classification will be wrong in the real world, because real scenes are messy. Birds, debris, sea clutter, and decoys can look similar. What that likely means is that future laser defense will be a software war as much as a hardware war, and software failures will be quiet until they are catastrophic. This is where people start saying AI will solve it, and we need to be careful. Better automation can help, but it can also create a new failure mode, humans trusting a ranking list that is wrong. A swarm is the perfect environment for automation to be tricked because it floods the system with near-identical inputs and forces rushed decisions. So the smartest approach is not blind trust, it is layered trust. Automation proposes, humans verify, and the system is designed to degrade gracefully when confidence drops. The rehook is sharp. In the laser era, the ship that loses is often the ship that shoots perfectly at the wrong targets. There is another layer people avoid talking about: rules and escalation. A laser can be a warning, a glare, a disable, or a kill, depending on power and aim. That flexibility is a strength because you can respond proportionally, but it is also a risk because proportional responses can be misunderstood, and misunderstandings start wars. What we know is that navies care deeply about identification and rules of engagement, especially in crowded regions where civilian traffic and military traffic overlap. What we do not know is how future doctrine will draw clean lines for directed energy use, because the effects can be invisible to outsiders and difficult to prove after the fact. What that likely means is that lasers will be used in ways that prioritize safety and clarity at first, which may reduce their tactical aggressiveness in some scenarios. This matters for swarms because swarms can hide inside ambiguity. If the defender hesitates, the attacker wins time. So the defense must be prepared not only technically, but procedurally. Who can authorize, how fast, based on what confidence, and with what fallback. That is not glamorous, but it is the difference between a weapon you own and a weapon you can actually use under pressure. The rehook is uncomfortable. The best laser in the world is useless if your decision chain cannot pull the trigger fast enough, and swarms are designed to punish slow permission. Now let's talk about countermeasures in plain language. If a laser is a lighter, then smoke is a hand placed between the flame and the paper. If a laser is a magnifying glass, then haze is someone shaking your hand while you try to hold it steady. The simplest counters are not science fiction. They are physics, aerosols, smoke, mist, reflective coatings, and movement patterns that spread heating. What we know is that many of these techniques can reduce effective laser performance, especially at longer ranges and in messy air. What we do not know is how well they hold up across different wavelengths and beam control methods, because that is a moving race. What that likely means is that attackers will combine cheap physical tricks with swarm timing to create a good enough shield, not to become invincible, but to force the laser into closer, riskier work. And this is where the swarm becomes truly strategic. The attacker does not need to build one super drone. It can build a menu. Some drones are sacrificial smoke makers, some are decoys, some carry the real payload, and some exist purely to force the defender to swing the turret repeatedly. That is like sending a crowd to block a door while a single thief slips through. The defense then has to identify roles inside the swarm, which is hard under time pressure. The rehook is cruel. Lasers can lower cost per engagement, but swarms can lower clarity per engagement, and clarity is what lasers demand. So, what does a laser-enabled layered defense actually look like in a fight? Picture 4 hands working together. Hand 1 is sensors. They build the picture. Hand 2 is electronic warfare. They try to confuse the swarm's brain and links. Hand 3 is lasers. They disrupt and trim the cheap mass. Hand 4 is missiles and guns. They finish the hardest threats. What we know is that this choreography is the most realistic path, because no single layer is perfect across all conditions. What we do not know is how well fleets can train this choreography at speed, because coordination failures are common when systems and crews are stressed. What that likely means is that lasers stop swarms will be true only when lasers are treated as part of a playbook, not as a solo hero. Here is a simple decision rule that feels like a teenager could run it on a whiteboard. If the target is low-end and within good beam conditions, use the laser to save missiles. If the track is low confidence or the air is messy, use soft kill first, dazzle and disrupt, and reserve hard kill for the clearest leakers. If the target is high speed or high consequence, do not gamble. Hand it to interceptors early. This is not perfect, but it shows the idea. Lasers are a budget tool and a time tool, not a universal tool. The cliffhanger is that the swarm's main job is to break this logic, to make every target look urgent and every second feel expensive. Now we do the cost math without pretending we know exact numbers. Missiles are expensive because they are manufactured complexity, and you lose one every time you shoot. Lasers are expensive because the system is complex, but the shots are mostly energy and wear. This creates a weird inversion. Missiles are high cost per trigger pull. Lasers are high cost to install but low cost to keep pulling the trigger. What we know is that this inversion is why directed energy is attractive against low-cost mass threats. What we do not know is the true lifetime cost per shot once you include maintenance, replacements, shipyard time, and training, because those numbers live inside programs. What that likely means is that lasers will be justified not only by dollars, but by inventory. They preserve missiles for the day you truly need them. And inventory is strategy. If you run out of missiles, you lose options. If you preserve missiles, you can fight longer and deter more. So lasers create deterrence by endurance. They help you stay in the fight without bleeding out your magazine. But the attacker has its own cost logic. If lasers lower the defender's cost per engagement, the attacker may respond by raising your time cost per engagement, more decoys, more clutter, more weather shaping, more coordination tricks. That means the next arms race is not only about hardware, it is about who can impose the more painful kind of cost, dollars, seconds, or attention. There is also the boring reality of reliability. A missile in a cell is a stored capability. It sits, it waits, it launches, and you are done. A laser is a living machine. Optics must be clean. Alignment must be precise. Cooling must work. Software must behave. And salt air tries to ruin everything. What we know is that complex systems fail in complex environments, and ships are among the harshest environments on Earth. What we do not know is the long-term reliability curve for every deployed configuration, because that takes years of fleet reps. What that likely means is that early laser doctrine will include redundancy and humility. Lasers used aggressively when available, but never assumed to be available. Training becomes a weapon here. A crew that knows when the beam is good and when it is lying will outperform a crew that simply trusts the label laser. The most dangerous failure mode is false confidence. When the ship believes it has infinite ammo and then discovers the system is degraded at the moment of need, that is why future readiness will look like checklists, calibration drills, thermal management discipline, and battle management practice, not just new hardware. The rehook is simple. The future weapon is not only on the deck, it is inside the crew's habits. Let's run a three-wave attack to feel the stakes. Wave 1 is cheap and noisy, dozens of drones, widespread, designed to force early engagement and burn decision bandwidth. In this wave, lasers shine, not as a miracle, but as a trimming tool. Blind some, disable some, force misses, and make the swarm less synchronized before it reaches the inner layers. What we know is that breaking coordination is often enough to reduce danger, because a swarm that arrives staggered is easier to manage. What we do not know is how consistently a ship can achieve that effect under mixed weather and clutter. What that likely means is that the first wave will be where lasers look most impressive on paper and most variable in reality. Wave 2 is smarter. It arrives as the ship is warming up, heat building, fatigue building, and track clutter still hanging in the picture. Now the attacker adds decoys and misdirection, and it tries to bait the laser into chasing the wrong targets. The defense must decide, continue hard kill and risk thermal limits, or shift to soft kill and preserve capacity for later. This is where doctrine matters, because a panicked ship spends its best tools too early. The cliffhanger is that Wave 3 has not even arrived yet, and if you have been tricked into exhausting your rhythm, the third wave will meet you at your weakest moment. Wave 3 is the one that changes hearts, because it brings a high-consequence threat inside the swarm. Maybe it is a faster drone with a heavier payload. Maybe it is a sea-skimming missile timed to arrive during maximum clutter. Maybe it is simply a coordinated multi-axis push that forces the ship to split attention. What we know is that real adversaries will not choose one threat type. They will blend them to overload your defenses. What we do not know is how well any single ship can hold a clean picture when low, slow drones and high-speed threats share the same minute. What that likely means is that lasers will be most valuable when they reduce clutter, because clutter reduction is what protects your ability to respond to the high-end threat. This is the key point. Lasers are not only about kills, they are about preserving decision space. If lasers can remove the cheap mass, the ship can focus missiles and guns on the few threats that truly require them. If lasers cannot remove the cheap mass fast enough, the ship may be forced to waste interceptors on low-end targets just to clear the screen. And that is how the swarm wins indirectly. The rehook is blunt. The swarm's dream is not to survive your laser. It is to make you spend a missile anyway. So what happens next if one beam is not enough? The obvious answer is more power, higher energy, tighter beams, better tracking, and faster target switching. But bigger beams do not magically remove physics. They raise the stakes of the same problems: air quality, thermal load, and system complexity. What we know is that the trend line in directed energy has been moving toward higher power classes and broader mission sets. What we do not know is how quickly that trend can deliver consistent performance against the hardest scenarios, because testing and deployment move slower than hype. What that likely means is that lasers will grow into roles gradually. First, counter-drone and soft kill, then stronger hard kill at closer ranges, and only later, if ever, true high-end air defense roles at meaningful distance. This gradual path creates a strategic gap. The attacker does not need to wait. It can exploit every interim stage. While the defender is learning, upgrading, and training, swarms can keep evolving. So the real future weapons question becomes, can the defender compress its learning cycle? Can it field upgrades, test them, iterate doctrine, and scale training fast enough to stay ahead of cheap adaptation? That is why this season matters. It is not about one laser shot. It is about whether the economics of defense can finally keep up with the economics of offense. There is also a different branch of directed energy that changes the one target at a time limitation. And it is not a laser beam, you see. It is energy that can disrupt electronics across a wider area. Think of it like turning on a very loud noise that only computers can hear. Instead of heating one spot, it can scramble many small systems at once, potentially affecting multiple drones in a cluster. What we know is that this concept is attractive specifically because it attacks the swarm's weakest common point: electronics and control. What we do not know is how it performs in complex environments, with hardened systems, mixed target types, and the risk of unintended effects. What that likely means is that future ship defense may combine precise tools, lasers, with area tools, electronic attack, and other directed effects to regain parallelism against parallel threats. But again, no free lunch. Area effects can be messy. They raise questions about what else gets hit, how you verify effects, and how you avoid harming your own systems or nearby friendly assets. That brings us back to trust and depth. Every new capability introduces new failure modes, and swarms are experts at finding those failure modes. The cliffhanger is that the most dangerous future weapon might not be the drone. It might be the moment the defender cannot tell whether its defenses are working, because the fight becomes invisible and electronic. So here is the answer to the episode question: how Navy lasers stop drone swarms. They stop them by changing what the swarm is trying to steal from you. In Season 2, the swarm stole your missiles and your money, one expensive intercept at a time until you ran out. In Season 3, lasers make the swarm fight for seconds, for air conditions, for track clarity, for thermal budget, for crew attention. What we know is that this shift is real. Directed energy can reduce the economic bleeding against low-end mass threats and preserve missiles for the high-end threats. What we do not know is whether lasers alone can keep up with the smartest swarms in the worst conditions, because the bottlenecks move, they do not vanish. What that likely means is that lasers are not the end of saturation math, they are the next chapter of it. And we leave you with the question that should start a comment war, because it is the question every Navy is quietly answering with budgets and shipyard schedules. If the swarm is a parallel threat, Do you beat it with more beams, better software, broader area effects, or a completely different defensive doctrine that makes the swarm irrelevant? In other words, do lasers win by killing more targets, or by buying enough breathing room that the swarm never reaches the point where it matters? Next episode, we go deeper into the most important piece people ignore. The real laser weapon is not the beam, it is the power system behind it. And the side that controls power controls endurance.